So Dante, maybe you can start by telling me how you got into your field.
Sure. I got interested in planetary science in 1992. I was an undergraduate at the University of Arizona, majoring in math and physics.
God, you're one of our own.
And I was working as a short order breakfast cook, which was a very hard job. And I saw an ad in the local student newspaper that said, "Come work for NASA." And it was a program called the NASA Undergraduate Research Space Grant program. So I applied.
Right.
I got accepted. I learned all about planetary science, and I decided to go to graduate school and pursue a career in that field.
That's great. That's a little connection we have, because when Gene Levy was the PI of that overall project, I was doing the intern program from 90 to 95.
Right, yeah. So
I probably saw your talk
exactly.
at the symposium.
I did a project on the search for extraterrestrial intelligence, working with Carl DeVito in the math department.
DeVito, yeah. Okay. Cool.
So even though it wasn't something that had a high scientific payoff, it got me thinking about extrasolar planets. In 1992, we hadn't really detected an extrasolar planet. We didn't know if planetary systems were common or they were unusual. What was the likelihood that life had originated elsewhere in the galaxy or in the universe, and particularly the evolution into intelligent life. So it really got me thinking about how would I tackle that problem. And I decided I needed to understand how planetary systems form. And at the time, we knew about one planetary system, that was our solar system.
Right.
So I started studying meteorites and piecing together the geologic story of our solar system.
So where did you go to grad school?
I went to graduate school at Washington University in St. Louis.
And then you came back right away here, or did postdoc?
I did a postdoc, and I became a staff scientist at Arizona State University. So I was up there for 4 years before I got hired onto the faculty here in 2001.
And still on friendly terms with them, I'm sure.
It's a healthy rivalry, but yes, we are working together. They are partners with us on the OSIRIS-REx asteroid sample return mission.
Right.
So yeah, we have a very healthy relationship with ASU.
So I want to ask about, because it's your specialty, why are small solar system bodies interesting? Why should we care? The big things get a lot of the attention.
Absolutely. So I'm very much interested in asteroids and comets, what we call the minor planets or small bodies of our solar system, because they record an era of solar system history that has been lost on Earth or on Mars, because these are geologic bodies, just like the moon. You know, it's been heavily cratered, and there's been volcanic eruptions. We have wind and water eroding the surface of the Earth. If we want to understand the earliest geologic history of our solar system, that record is only preserved in the small bodies, which have basically, they formed within the first 10 million years of the evolution of our solar system, and in some cases have remained unaltered since that time.
So that is 10 million. That's very primordial. I mean, that is also amazingly rapid that they formed that quickly. Yeah,
well, we think the Earth formed within 30 to 60 million years after the first solids in the solar system, so we had planet-sized bodies very quickly. So yeah, the initial history of our solar system, there was a lot of chemistry, a lot of dynamics and physics going on, and particles from dust grains up to planetary-sized objects were forming within tens of millions of years.
Now, I know when people first they think about comets and they see pictures and they sort of understand the elliptical orbits, but when they truly realize that there are a trillion of these things, mostly at huge distances from Earth, far beyond the orbit of Neptune, so on, they wonder, as I did when I first heard, how did that happen?
Right.
Where did the comets come from, or how did they form in such a strange place and way?
Yeah, so the long period comets come from a region we call the Oort cloud, which is almost a spherical distribution of icy bodies that goes out pretty much from the sun to halfway to Alpha Centauri, where the sun's gravitational field starts to compete with that of other stars. But they didn't form out there. I mean, as the solar system was forming, it formed through the collapse of a giant molecular cloud, a giant cloud of gas and dust where many hundreds or thousands of stars formed at the same time. And as that cloud collapsed, a property called angular momentum was conserved, which is basically the energy in the rotation. And so that material went from a cloud into a disk, and we spun out a disk of material, most of which was falling into the central protostar, which would go to grow into our sun. But a lot of solid materials formed in that disk and accreted into our planets, and that's why we find our planets are pretty much in a single plane with very low inclination variations. However, once you had big, massive planets like Jupiter and Saturn, they had enough gravitational energy so that they could take small bodies, icy bodies, or rocky bodies, and fling them into these high inclination orbits and basically throw them almost out of the solar system, but with just enough energy so that they were still gravitationally bound to the sun, and that formed the population of long-period comets in the Oort cloud.
And when we say long period, what are we talking about?
Tens of thousands to hundreds of thousands to millions of years for a single orbit around the sun.
And so the vast majority of them never come anywhere near the Earth, right? The comets that people think about that we see photos of occasionally are this tiniest fraction of the population.
That's right, yeah. Very few of them come into the inner solar system. Some of them, they're coming in for, only a few times into the inner solar system when we see them. And they won't be seen again in human history, probably.
Now, when you talk about formation, one of the things I recall is people speculating that the formation of our solar system was triggered by the death of a nearby star, and there was some tentative evidence that might be true. Is that still a story that people talk about?
It is. There's a couple reasons we think that. First of all, most stars form in what we call high-mass star-forming regions, and so you get large stars that form quickly. They run through their lifetimes in tens of millions of years, and they explode, and that energy ripples out through the clouds around them and may in fact trigger the collapse of the cloud like we were talking about earlier. But we have some geochemical evidence that also supports that idea, and that's in the fact that there are certain isotopes that are radioactive that only form in supernova explosions. One of the key ones is an isotope of iron called iron-60. It has a very short half-life on the order of a couple of million years, yet we find evidence for it getting incorporated into the first solids that formed in our solar system. So that means its source had to be relatively nearby. So you had to create that iron, radioactive iron, in a supernova, or I should say a giant star that then exploded in a supernova, injected that radioactive material, got incorporated into the solid before the decay was complete. So that's really good evidence for a nearby supernova.
Wow. And of course it's an elegant piece of the whole idea that, we're seeded with the dust of previous generations of stars anyway.
Right. We know that to be true. When we look at some of our primitive meteorites, which are fragments of asteroids that have landed on the surface of the Earth that we can study, we find a substantial population of pre-solar grains. And pre-solar means grains that formed before our solar system did. And they come from a wide variety of stars, from supernova, from asymptotic giant branch stars. So we see that there was all kinds of stars that were throwing off material into the interstellar medium. That material condensed into grains, and those grains survived passage for millions of years and got incorporated into our solar system, preserved in these small asteroids, survived 4.5 billion years of solar system history, landed on the surface of the Earth for us to get them into our laboratory and study them. We call it laboratory astrophysics.
So you're not just a space cadet, you're a lab rat as well.
I am basically an analytical chemist. Right. That's what my background is in, and I apply those skills to studying primitive meteorites and understanding the early solar system.
On a couple of questions, when we talk about unaltered bodies, how do we know they're unaltered? What is it that tells you it's truly pristine or primordial?
Right. So the first thing we look at is the chemistry, and we have a population of meteorites we call chondritic meteorites, and they are called that because when we look at their composition, for everything except material that forms ices, which wouldn't be preserved in stony material like this, or noble gases, which are always in the vapor phase, we look at the abundance of the rock. We can look at the abundances of the elements in the sun by looking at the photosphere, and there's lines that are characteristic of different elements in the spectrum of the sun, and we can determine their abundance. The most primitive meteorites have the exact same composition of the sun, with the exception of those that form ices and those that stay in the gas phase. So basically we have rocks that formed from material that formed the sun. So that tells us it's very primitive. Because as soon as you start any kind of geology, like melting or thermal alteration, those elemental ratios get changed, and they're no longer primitive in that sense. The second thing is looking at the texture in the mineralogy. These rocks are the equivalent of sedimentary rocks. So you go to a stream bed and you scoop up a bunch of particles from that, and you look they're not really related to each other. They could have formed from anywhere in the mountains that are way up above that stream bed and just got transported down. And so you could have 10 different rock types easily represented there. When we look at these meteorites, their particles formed over millions of years. Their ages are very different. Their chemistry is very different. They appear totally unrelated to each other. They're the equivalent of space sediments. So they just swept up all of this dust from the earliest stages of our solar system history that got compacted into a rock and basically left unperturbed since that time.
And as I recall, I mean, the age of the Earth, the solar system, is now a pretty precise number, like third decimal place.
That's right, 4.568 billion years.
And we can really talk about that third decimal
We
place.
can really talk about that, and we can argue about it, and we can use that third decimal place to determine the relative age of those different components. So yeah, we date the oldest solid material in meteorites using uranium-lead radioactive decay systems to that third decimal point, and those are the oldest materials that have ever been dated in a laboratory on Earth, and therefore they determine what we call the T0 age of the solar system. There's nothing that's older than that we have in our laboratories.
And I guess you have so many species, parent daughters, that you've got lots of cross checks on this. That's pretty heavily laced, webbed by evidence.
That's right. Yeah, it's very self-consistent, and so we use those long-lived isotopes to get an absolute age, and then in order to determine relative ages, to check that third decimal place, we use things like iron-60 or aluminum-26, which were radioactive in the earliest history of the solar system, but have now completely decayed. But we can say that something formed 2 or 3 million years after something else by the abundance of that isotope that it collected.
Okay, well, I want to get to why we don't just subsist on free samples and why we want to get real samples, but just as far as what are the most useful meteorites for learning more from now, their various classes and subclasses and so on, but in the profession, what are the ones that are still giving us useful information?
Well, I would say every meteorite is useful to somebody because there's different processes that they record. For me personally, I like those sediments that we talked about, the ones that really record the earliest processes in our solar system, and I'm even more interested in a subset of those, carbonaceous chondrites that are rich in organic material and seem to have accreted a lot of icy material when they first formed. That ice has since melted and reacted and created clay type of minerals. So I'm asking the questions going back to my search for extraterrestrial intelligence. Not only am I interested in how the planets formed, but I'm interested in how did the Earth form with such an environment that was conducive to life and to evolution. The first thing you got to understand is, why do we have water on this planet? Where did our water come from? It probably wasn't here when the planet formed originally. It was too hot in the inner solar system. That water had to be brought in, and we argue about whether it was brought in by comets or whether it was brought in by these hydrated asteroids. Probably both contributed different amounts to our budget. Then I get interested in, once you've got water and stable as a liquid on the surface of the planet, how did you create life? And when we look at some of these meteorites, they turn out to have a lot of interesting organic material, like amino acids and nucleobases that are the basic building blocks of all of the molecules in our bodies, like proteins and DNA and RNA. So we want to understand the earliest organic chemistry, and basically, did the seeds of life get delivered to the surface of the Earth from asteroids that then led to the beautiful biosphere we have today?
So it's a nice kickstart. And I read, I don't know if the number's correct, something like 100 amino acids in the Murchison meteorite.
A little less, on the order of 80 or so, I think, is what we've identified.
Which obviously include a lot that are not the basis of our biology.
That's right. So that's one reason we know that they're not terrestrial in nature, because there's plenty of amino acids in the meteorites that aren't used by life. And it's also an interesting question. So you form this great diversity of amino acids. How did life select for the 20 or 22 that are used in proteins today?
Right. And we don't. It's an open question.
That is an area of active research, absolutely.
And another, maybe this is not true, but I heard that another interesting chemical issue is phosphorus, because ATP is an engine of life, if you like. And the phosphorus abundance, did that also depend on extraterrestrial material deposition?
Yeah, we did a lot of research on that in my research group over the past decade or so, and it turns out there are minerals in meteorites that contain a lot of phosphorus, and they're a rare group of meteorite minerals called phosphides, and we did experiments where we took those minerals, we put them in liquid water, very simple experiment, And we looked at what happened to the phosphorus, and it turns out it goes into the liquid, and it forms all kinds of very complex molecules very easily, even just with the phosphorus and the oxygen. You mentioned ATP. Phosphorus is also critical to DNA. It's basically the backbone with sugar of the DNA molecule. So it's very important to get into the origin of life. How was phosphorus introduced? And meteorites offer a very reactive source of phosphorus if it gets introduced to liquid water.
Now, I guess the biggest amino acids are 20 or 30 atoms. I mean, are there other, more even larger organic or complex molecules in?
There are. In fact, the most abundant organic material in meteorites is more like a kerogen, kind of like a tar material. But that's not very interesting for the origin of life. Making a tar is pretty easy to do, it turns out.
Because it's unstructured, or what?
Yeah, it's bound up, and it's, you know, you imagine how hard it is to deal with a tar. You know, you're interested in something that's highly soluble in water and can then go through a series of chemical reactions. These are highly insoluble. In fact, the way we found them is we took meteorites, we dissolved them with the harshest acids that we have in our laboratory, and we looked at the residues that were left, and it was this macromolecular organic material. So once it's in that form, it's pretty unreactive.
Okay. So beyond the amino acids, are there any other interesting ingredients that are, you know, that are part of the story of formation of life?
Yeah, you need the amino acids, you need the sugar, you need the phosphates, and you need the nucleobases, basically the letters of DNA. And we find all of those in meteorites in different abundances.
Wow, okay. And by implication, comets, or we don't know?
We don't know because we're not sure we have samples of comets in the laboratory for analysis, right? Because they're icy bodies primarily, so even if they were to survive the passage through the Earth's atmosphere and land, they don't stick around long enough for somebody to go out and find them. The nice thing about a meteorite is you can go out months after the meteorite fall and still pick up pieces of it. That's not true for a comet. We have never gotten a piece of icy cometary material into our laboratory, so we just don't know. We don't have the capabilities to do that right now.
Right. So given that there are all these free samples, well, I'm sure you can tell me the flux. What's the flux of meteorites falling on the Earth, roughly?
On the order of tens of thousands of tons of material every year come onto the Earth.
Most of which is unrecognizable.
Yeah, most of it's really fine dust and creates the shooting stars or the meteorites that or meteors that we see in the night sky. So they don't make it to the surface of the Earth. But we get well over a dozen or 24 meteorites that are recognized, that fall on Earth, that are picked up and brought into our laboratories every year for study.
And that has to be quick, right, because of contamination?
It doesn't have to be, but they're most useful if they're picked up quickly. And of course, those are just the ones that land on the continents. The ones that land in the ocean, those are just lost to us forever.
Right. So given all these free samples, why would we go to the time and expense of going out in space for samples?
Great question. So there really are two reasons we want to go to an asteroid and get material and bring it back to Earth. The first is the geologic context of that material. We really have no way of linking the meteorites that we find on Earth with a particular region of the solar system where they came from. Really, with one exception, that's the big asteroid Vesta, which the Dawn spacecraft just finished its visit to. Got some great information. We do have meteorites that we can link through their spectral properties, that is how they interact with light, to the surface of Vesta and say these are probably from that single asteroid. But they're very distinctive minerals that make it easy to make that connection. For these carbonaceous meteorites, they have basically no features spectrally. They're black, they're flat, so it's hard to connect them to an asteroid. We think we can do it, but we want to make that connection really tightly so that we can understand the distribution of this material in the solar system. We also want to understand where on the asteroid the material is coming from and what that can tell us about the history of that asteroid. You know, we're interested in near-Earth asteroids for their science value, but we're also interested in them for their resource potential, and we're interested in them because they represent an impact hazard. So we want to understand the material properties right at the surface of that asteroid. And so we can do that by getting that sample back to Earth. It turns out its thermal characteristics are really important for the orbital evolution of an asteroid. We're going to study that in great detail. So geologic context is something that we're completely lacking in our meteorites that we will gain with an asteroid sample return mission.
Oh, and as an aside, that's exactly the argument for why we want Mars sample return too, right?
That's right.
We got, what, how many Martian meteorites?
It's growing all the time. I can't keep up, but last count was well over 80 Martian meteorites.
But they're just not as useful as a rock you could bring back.
That's right.
From a
and
known location.
we don't see the sedimentary rocks on Mars represented in our meteorite collection. And same thing with the asteroids. The most fragile, friable material is probably the most organic rich and the most clay rich. That doesn't survive passage through the atmosphere very well either.
Right.
So the most interesting stuff scientifically is probably destroyed as it passes through the atmosphere of the Earth. So we have a chance to get it. The final piece of that is we want something that's really pristine. We're interested in the amino acids that are used in biology, and we're interested in the nucleobases that are used in biology. But it's actually a hard problem to solve looking at the amino acids in meteorites to figure out their abundances in those meteorites because they're very quickly contaminated, colonized by bacteria. They're picked up in remote locations under uncontrolled conditions most of the time. So the compounds that are most interest to us are the stuff that's all over the surface of the Earth and contaminates the meteorites very quickly. We are spending a lot of time and attention on OSIRIS-REx to control the contamination. I look at it as a forensic investigation. I'm making an argument that this material originated in outer space. In order to do that, I have to have control of the evidence from the time it left the surface of the asteroid until the time it got into my laboratory, and I can only do that if I collected it off the surface of the asteroid, brought it back, and got it into a clean environment as quickly as possible.
Now I want to get to OSIRIS-REx, but you were involved heavily in Stardust as well, right?
That's right.
Talk a little about that. That was a neat mission.
That was great, and I didn't get involved in the spacecraft side of it. I was on the ground waiting for the samples to come back and get them into our laboratories to understand the history of comet dust. So Stardust was a mission that flew through the coma of Comet 81P Vilt 2, and it stuck out a grid of aerogel, which is a really low-density material. It flew through that dusty region around the nucleus of the comet, captured thousands of particles that were streaming off of the nucleus, and then put that grid into a return capsule and dropped that capsule back to Earth in the Utah desert. So we went in and looked at a specific type of mineral called the sulfide mineral. And they're really interesting because, first of all, they're common in meteorites, but there's a wide range of different compounds. And it turns out the ones that we found in the comet were very rich in copper, in a rare copper-bearing mineral called cubonite, and it turns out those only form in liquid environments. So we had found really strong evidence that there was liquid water active in the interior of this comet at some point in its history, and that really was a big paradigm shift for comet scientists who thought that these were basically deep freezers from the outer solar system. And the prediction, and the reason the mission was called Stardust, is we thought that it would be full of these pre-solar grains I talked about earlier, that they would represent the dust of the interstellar medium that didn't get processed in the solar system at all. Turns out that is not the case. We're struggling to even find a single pre-solar grain in the Stardust collection. And in fact, the grains look like the stuff in our meteorites. So all of a sudden, comets now look like asteroids, and asteroids now look like comets. And in addition, we found the liquid water was moving around inside the comet and altering these minerals. So these are geologically active bodies, and the solar system was a really dynamic place. The dust got spread everywhere out to the Kuiper Belt where this comet originated from.
So there's a huge amount of mixing going on.
Huge amount of mixing, and it turns out that we're realizing that there's not asteroids and comets as two distinct kinds of bodies. There's a continuum where you have stuff that's almost completely rocky and metallic material, that's your most dry asteroid, all the way to something that's pretty much completely ice and the most cometary-like, but you've got everything in between.
And what did it do, having this sample must have put some information on the table for where the water came from on the Earth, say, did it?
Well, we didn't capture the ice from this mission, you got to remember, so we only got the dust grains. So the key information there is the isotopic composition of the hydrogen in the water. We weren't able to measure that from Stardust, so we couldn't address that as a big issue right now. Where did the water come from?
So let's get to your mission. And I mean, a sad starting point, the loss of Mike Drake, which is we're all very sad about.
Absolutely. So we won the OSIRIS-REx mission, and it was a competitive program inside NASA called the New Frontiers program, where dozen or more teams were competing for this funding to build their spacecraft and fly their mission. Mike Drake, who was the director of the Lunar Planetary Lab prior to his passing, approached me in 2004 about getting involved in an asteroid sample return mission concept. And we ended up bidding this project 3 times to NASA, and the 3rd time was the charm. The 3rd time was when we won. So
and you were pretty junior, right? You were just tenured, or
I wasn't even tenured when we started. I was hired in 2001, wow. So when I started, I was 3 years into my assistant professorship here.
That's a pretty intimidating thing to take on.
It was a big risk career-wise. I certainly gave up a lot of time that would have been spent writing journal articles, winning proposals, writing papers, all that stuff. I had to put a lot of that aside to focus on winning the project. So we worked together very intensely for 7 years before we finally won the contract from NASA. It took a big toll on all of us. It took a toll on Mike. He ended up with liver disease, and he ended up passing away in September of 2011. So right after we got started, we lost Mike. And I was his deputy throughout all of that, and I ended up stepping into the role of principal investigator at that time.
So, paint a picture of the timeline for people who do science projects. They get a 3-year grant or a 5-year grant, and they think that's a big commitment.
Right.
Talk about, you just said 7 years before you got a green light.
That's right.
How long till you get your samples, and then you're studying them.
Right, so here we are
lifetime.
We're in April of 2013, so we've basically been working for 2 years now since winning the contract. So we're at a period called confirmation. So we just finished a huge set of reviews for NASA, and now they're deciding whether or not we get the money to start building the flight hardware. So it's a much bigger dollar commitment on the agency's part. The good news is our reviews all went extremely well. Confirmation looks like it's going to be no problem for us. So from that point forward, we're looking at about another 3.5 years till we launch the spacecraft. So we'll be launching in September of 2016. So it'll be about 5 years from selection to actually having a spacecraft in outer space, and that'll just be on its way to the asteroid.
I'm keeping track. That's 12 years so
far.
far.
It's a 2-year journey till we get to the first look at the asteroid. We're hoping that we can survey the asteroid and find a site to get a sample within about 300 days, so a little less than 1 year.
And that's tricky because you can only plan so much that phase. You just don't know, right?
That's right. I mean, we're explorers. We're going out to an asteroid that we know a little bit about from telescopic characterization, but we don't know the details that we need to get a sample. So we have to basically survey the whole asteroid, find the site to get the sample. We'll send the spacecraft down to the surface of the asteroid, contact it for about 5 seconds, grab a sample during that time, and then get away from it. That's
5 seconds?
5 seconds on the surface of the asteroid. So we hope that happens within about 10 months. The good news is we've got over 1,000 days at the asteroid, so we've got a lot of time if we need it to really make sure we get the sample. So we'll arrive in 2018. We can't leave until 2021. That's just when the planets line up again and we can start our outbound return home. We get back to Earth in 2023. So it's 7 years from launch until Earth return. And then we have funding for an additional 2 years of science to study the return sample. So the end of the mission is in 2025. So I started this journey in 2004, trying to win.
Wow.
My funding runs out in 2025, so I was...
You know what you're going to be doing.
That's right. We hope. I mean, everything goes well. We've got samples on Earth in 2023, and then the real fun starts. Then I'm back to my roots.
Now, I remember talking to Carolyn Porco about for Cassini, and she just analogized it to child rearing. You have the excitement, disappointment, a 20-year commitment, and that's the deal.
It's a very good analogy, and the fun part is my first son was born in 2006 after we won the first concept study money from NASA. So my children and my spacecraft are growing up together.
Right. And they'll just leave home probably around the time the samples come back.
Exactly, yeah. They'll be on their way to college when the samples come back.
So talk about one issue that I know people think about when you bring back extraterrestrial material to the Earth, and I know NASA's pretty sensitized to this because I've seen facility at Johnson where the moon rocks are kept. So what's the level of concern about contamination?
We are not concerned because this is a near-Earth object, so it comes very close to the Earth repeatedly. So, in fact, it has a reasonably high probability of hitting the Earth someday. So it's not something that has a high biologic potential. For in extraterrestrial biology, we're not really concerned about. It's also an ancient rock, so any biology would have been extinguished 4.5 billion years ago, and the radiation exposure since then is enough to sterilize it. So we went through the planetary protection review process with NASA, and we've been classified as unrestricted Earth return. So we don't have to have any kind of hazard containment facility for the samples. Just the standard clean techniques that we need for our science, because we want to keep that sample organically pristine.
And was that true for Stardust for the same reason?
Yeah, Stardust was the same.
Okay, so that's actually not a big set of hoops you've had to jump.
Yeah, we're not worried about bringing back pathogens from outer space on this mission.
I mean, and I know some of it's bureaucracy and not interesting, but talk about just running a big project. I mean, you must get tired of the jokes of being the $800 million man, but apart from that, I mean, what are there must be good parts and bad parts of
there are. It's a far cry from being a scientist in many ways. I look at myself now as basically 1/3 scientist, 1/3 spacecraft engineer, and 1/3 senior management. So I spend a lot of time worrying about money and about schedule, people. We've got, at our peak, we're going to have about 500 people working on this project. About 100 of them here at the University of Arizona, including a lot of students. And you learn how to manage people, personalities, morale, the problems that people encounter in their personal lives and how you accommodate that on a very busy schedule so that they can take care of their families and take care of themselves. Those are all skills that I've had to really learn kind of on the job so that we can be an effective team. And then the engineering side of it. So one thing you learn right away is not to let the science team run wild with requirements or desirements and things that they want to do. Because it's very exciting
Some
for
of
us.
which you want to do, too.
That's right. We want to get out there and we want to do everything we can possibly do with this asteroid. But you start to see how something that sounds very simple when the scientists sketch it out on the whiteboard and the engineers then sit down and start to design the system to do that, you're like, geez, that's going to cost $20 million at the end of the day. It's like, okay, guys, we can't afford that, so you got to push back on that. You got to figure out $800 million sounds like a lot of money, and it is a lot of money, but you want to use it wisely. You can waste a lot of money very quickly on a mission like this if you don't control your requirements. So I spend a lot of time interpreting science to engineering and engineering to science so that everybody understands the limitations and the capabilities and what we really need to get done to bring a sample back to Earth.
And it seems like with this project, as with Phoenix before, I mean, NASA's really devolving a lot of the mission to the university and to university scientists, which is probably a good thing, right?
It's a great partnership. I mean, the mission is really the primary partners are the University of Arizona, and we bring the science expertise, but we also bring the instrumentation, observing asteroids, building cameras, and then processing scientific data. We've got our project management and engineering at the Goddard Space Flight Center, and they're valuable members of the team. They know how to handle all the NASA reporting requirements, how to make sure we maintain compliance with all the NASA regulations, and then they manage the big aerospace contractors, and our prime partner in the aerospace industry is Lockheed Martin. And they're the engineering organization. They know how to build a spacecraft that works in outer space and does the job that it needs to do. So it really is those three pillars that bring very different experience and capabilities together to make a mission like this a success.
So you can probably pick a couple, but there are going to be some nail-biting moments, right? Which are the launch, I suppose, and which are the nail-biting moments in anticipation?
Launch is the big one, right? I mean, that's because it's almost out of our control. We are not responsible for developing the rocket. We show up, they put us on top of the rocket. Some other team has spent their past 5 years building that rocket.
And you don't have a spare sitting in a garage somewhere.
We do not have a spare. We are what we call a proto-flight program. We build and test the flight unit and send it into outer space. The good news is we're on an Atlas V launch vehicle, very reliable, very low probability that we're going to lose the spacecraft at launch. But still, you're sitting on thousands of pounds of explosive, sending this thing into outer space. It's a tense moment, but a very exciting moment. The next one for me is when we actually see the asteroid, because we've been coming up with all these scenarios, how we're going to get a sample. We have some preconceived notion of what this asteroid looks like. But we're going to get those first pictures back, and nature has a way of surprising you.
Mm-hmm.
You know, does the system that we built have the capabilities to get a sample off this body or not? That's the first assessment that we're going to be able to make.
And even backing up a bit, you're not worried about reconnoitering with the asteroid, that, you know, the rocketry of that. That's
pretty straightforward. We know where this asteroid is very well. We've observed it many times with the Arecibo Planetary Radar System. We have its orbit nailed down. We know where it is in space. I'm not worried about getting there.
Right.
I'm worried about what we're going to find when we get there.
Right.
And then, of course, that 5 seconds of contact, right? We would have just spent, at that point, 14 years, you know, from concept to getting to the asteroid and getting that sample. And we have 5 seconds to get the material off the surface of that asteroid. Everything comes down to that moment, getting onto the surface, grabbing that material, and then making sure we got what we need before.
How much?
The minimum requirement is 60 grams, about 2 ounces of material, which for a sample scientist is an enormous amount. We can study that for 100 years and still not learn everything we can learn from the material. But our capability is much higher than that. We'll make hundreds of grams of material.
And what's the mechanism?
So we're using a touch-and-go sample acquisition mechanism, or TAG-SAM we call it. It has 2 techniques for getting material. The first is it's got a series of contact pads around an outer ring. So just by making contact with the asteroid, we'll pick up particles that are millimeter size and smaller and get those back to Earth. But we're not going to get 60 grams of that. That's kind of a contingency. As long as we touch the asteroid, we'll get something off the surface and bring it home. What happens after we make contact is we open up a high-pressure gas bottle and we blow down nitrogen, high-purity nitrogen gas into the regolith, or the soil, on the surface of the asteroid. And it basically explodes in a big cloud of entrained material. And we've got a giant air filter sitting there to catch it all.
Okay.
So we get that. It's a very clean technique. There's no moving parts, greases or oils or anything like that to interfere with our organic analyses. And that's where we pick up the hundreds of grams of sample in that very short time period.
And obviously you've modeled it or have expectations, but your yield depends on the nature of the surface.
It does, absolutely. How deep is the regolith? How coherent is it? You know, what's its cohesion? So a lot of that is model dependent. That's right.
Is there a maximum? I mean, is there an amount beyond which you can capture it?
If we pack the filter full of rocky material, it's about 2 kilograms.
Wow. Well, that would be amazing.
That would be a lot of samples.
What would that say about the surface if you got that much?
It would say that you had a very deep bed of regolith that was loosely bound together and very easily mobilized by that. And within the test where we pack the filter head, usually we sink in, you know, so that the filter is completely buried in the material, and so all of the gas goes into driving material into the filter. Nothing shoots out the sides or gets lost as a result. It's complete efficiency of the system.
Right.
So after that, we have to come home, and the last nail-biting moment is that capsule gets pushed off the spacecraft. We're targeting the Utah desert, same place the Stardust capsule landed, but we've got to come through the atmosphere. We're coming in at about 12 kilometers a second. The parachute has to deploy.
Right.
There was a mission called Genesis, where it turns out the parachute switch was installed backwards, and so the parachute did not open up, and that capsule came in for a hard landing and shattered in the desert when it landed. So that's the final nail-biting moment, is that parachute opens up and the capsule glides gently down to the surface of the Earth, and then we can get out there, recover it, and get it into the Johnson Space Center in Houston to open it up and see what we got.
So that's where you'll be.
I'll be there in Utah.
What day is it? You know
that is September 24th, 2023.
It's amazing to have something on your calendar that far ahead.
That's right.
It's a non-negotiable.
Non-negotiable.
Sorry, I'm turning down speaking engagement.
Yeah, that's right. That's right.
Okay. And how many groups? Say it's near the smaller amount of that range of that material. How many groups are going to be vying for a bit of it?
We expect hundreds of laboratories around the world requesting material from NASA for analysis, and 60 grams is enough for everybody.
So you're not going to have to make brutal decisions about some people getting nothing, or...
That's right. This is so much material. I mean, Stardust didn't even bring back a milligram, and it was studied in over 150 labs within a month of its Earth return. So we have gotten machines that can image down to the individual atomic columns of a crystal from these bodies. So yeah, when you're looking at that scale, it's an infinite landscape to study.
Right. Which is, of course, is an important aside for astronomers who just do remote sensing and that's all they can do, is that's the value of having the real stuff.
Exactly.
Going into the lab.
Exactly.
So, well, I want to wrap up. That was great. Is there life beyond OSIRIS-REx? I mean, you're not going to be that old when it's done. Can you
I will be
imagine?
52 years old when that sample comes back to Earth, so
And you're
hopefully I'm
obviously
still in
gonna
my prime.
You're going to want to probably spend more than 2 years working on the samples.
I'm excited by the opportunities and the initiative that I see for exploration of asteroids. I mean, now we've got companies in the United States that are incorporating with the objective of exploiting asteroids for economic minerals and life support components. We've got NASA looking at sending humans to an asteroid or capturing an asteroid and bringing it back to the vicinity of the Earth. The technologies and the operations protocols that we're developing on OSIRIS-REx are going to feed forward into all of those missions.
Right.
So I hope that this is not a one-off science mission, but really the opening of a new frontier.
Wow. So that's it. I can just see you as the chief scientific officer of a new commercial entity, in 2025 that's actually really going to
Fingers crossed,
do
right?
this on a large scale, because government-sponsored research can only do so much.
That's right. We should be the pathfinders. I mean, government should be developing the techniques and technologies and then transferring that over to the private sector for true economic development. I would love to see that happen.
Right. Okay. Thanks a lot, Dan.
Yeah, thank you.